Hi everyone, this is Mr. C, and I'm going over the lesson that I did in class today. This is still under the description of forces in two directions. Okay, we're just starting forces now, and I want to show you how the little demonstration I did in class worked. You should have complete notes on it, but this tutorial is intended to supplement those notes. Now we're going to use gravity as 10 meters per second squared for this demonstration, just to make the math a little bit easier. And what you see on the screen is the same thing we had in class. We have a pulley. It's a frictionless pulley. Its only job is to change the direction of force. Okay, and we're going to call that force tension Ft right here. And it's going to be equal to whatever was in the cup. Now in class we measured it, and let's say that we had 10 newtons in this cup. Okay, and that's the force of gravity of the cup, which is the same as the weight of the cup. So we have 10 newtons pulling down. Now recall in class the configuration we had. We had a rope coming right across, and we had another bucket full of washers, and we didn't know what the value of those washers was, and that was the job that we were trying to do. Okay, so this is how we had it set up in class, and we had that rope tied to the wall. Now, recall also that this rope over here, it's all one piece. Okay, here's the bucket pulling down, that this was horizontal. Okay, and I'm just going to put horizontal over here, and then I'm going to erase it. Just so you know, this was horizontal, this rope right here. Okay? And that's what it looked like, and it was tied right to the wall over there. All right, so what was the first thing we did? I'm going to try and do this in steps, because as I was doing it in class, I told you that I would record this, and we will use the steps that I'm going to illustrate right now. So let's, and you don't have to use all these same steps. Okay, so let us go on. The best place to start with steps is step one. So let's see what we can put down for something that we will use as our rules all the time. Let's call this, let me get my pen ready here. We're going to call this step one. And we kind of, looking at this, you can see what our objective is. Our objective is to try and find out the unknown weight of the bucket with the washers in it. And you recall that I picked the washers randomly, I threw them in the cup, and we measured this cup, and we had no idea what this was going to be until we did some calculations. So the first thing, let's draw a free body diagram, an FBD. Okay, and I want to change the colors a bit because I want this free body, I want you to know where I'm drawing it from. So this free body diagram is going to be the equivalent of this spot right there for our unknown. So let's draw that spot. Okay, spots are easy to draw. Okay, there's our spot. That's where I want to know what's happening. Now before we draw this, let's observe a few things. In class, was this spot moving? Was it accelerating? Was there an acceleration? No, there was no acceleration. Okay, remember Newton's second law. And matter of fact, there was no velocity at all, but there was certainly no acceleration. And Newton's second law said acceleration was equal to force net, all the forces added up, divided by the mass. Okay, in this case it's going to be the mass of the bucket. Alright? But if there is no acceleration from this point in orange, then there must be no force. All the forces adding up must be equal to 0. So that's our first observation when we're looking at the free body diagram. Okay, I accidentally erased my little orange dot, so let me put that back on here. Okay, and we're talking about this point right there, which is the equivalent of that point right there. And let's draw all the forces we possibly can to see what forces are easily observable. All right, so let me go back to here, and let's see. We got a force going down, I think, don't we? Sure we do. We got a force going down toward the center of the Earth. We're going to call that the force of gravity of the bucket, which is equal to the weight of the bucket. In case you've forgotten. Okay, and this is what we're looking for. We don't know what that is. Better put a question mark there. We don't know what that is. That's our goal, to find out what's in that bucket. Now we also have another force. Okay, and that's that force that I can see right here pulling up right there. Okay, nice. What a pretty color that is, huh? This force is pulling up like that. Well, let's see if we can draw that force. Okay, I'm right here. Try and get it about right. And let's draw that force coming up like this. Okay. And that force, what should we call it? Why not call it what it is? It's the force tension. Force tension. Okay. Well, are we all done? Well, not really. I see another force coming off this point. I see coming off that point, one, going down, we got that, the force of gravity of the bucket. We have the force tension. What's this over here? Let's change the color again. What's this guy right here? Ah, the force tension 2, the one that's tied to the wall. So let's go back and draw that one as well. Okay, and I'm going to draw that one going right across like so. Okay. Force tension 2. Force tension 2. Let me clean that up. Force tension 2. Okay, so those are all the three forces. Now we agreed that all the forces must equal 0 because this spot, the orange spot, is not moving. Okay? That spot is not moving, and those are all the forces that are shown. Okay, let's just focus for the time being on the force tension and this guy coming down. Now, that's the force gravity. I want to put this on something called a coordinate system, which you know what it is. A coordinate system is nothing more than an XY. I'll do it over here. It is an XY let's see. Oh, there's one. Let me undo that. Didn't come out quite the way I had hoped. Okay, let's try this again. Let's draw a couple of lines, one going straight across this way. It's a coordinate system. There's the x-axis, and here's my y-axis. Okay, now I'm going to label those so we can remember what a coordinate system is. It's nothing more than a map. It is nothing more than a simple map to help me put things in a way that I can see them real easily. And we know this is the y direction. If that's the y, this must be the minus y. And if this is the x, this must be the minus x over here. Now I'm going to lay this coordinate system right on top of my forces. Okay, let's see if we can do that. I'm going to take this guy and put him right across like like that. Okay? And I want to move, let's see, let's move this guy out of the way, put this over here like that, and overlay this right on top. Okay, it's going to be a little hard to see, so I'm going to displace it a little bit. So that's one direction, and now I'm going to take this guy and overlay him right like that, and that's our coordinate system. Okay, I'll clean that up in a second. This becomes our y-axis. This is our minus y-axis. This is our x, and this is our minus x. Okay, I want to focus on this force tension. That's what I said before. I showed you in class a little demonstration. What I did in class, and try and recall this, is I had a stool. And let's make that stool look like this little object right here. Okay? And in class, I pulled on that stool in two directions. I pulled on it. A matter of fact, you guys helped me. I pulled on that with a force in this direction with a rope. I connected a rope to the stool. This is a top view, by the way. We're looking down on it from the ceiling to the floor. And I pulled on it in the other direction like this. You guys did it with me. Okay, let's see. I did it down in the other direction like so. And we pulled with equal forces in both directions, and wouldn't you know it, the whole thing moved like this. That, not the whole thing, the stool actually ended up moving like so. Okay, it didn't go this way, it didn't go that way, it pulled like this. So it was easy to see that this vector up on top and this vector summed together and gave me a resultant. Remember what a resultant is. The end result was the way this guy was flowing. So in effect, remember how to add vectors, tail to nose? Okay. This is what I had for the equivalent force when I was done. The blue was the equivalent moving in that direction because I added the two vectors. And do you remember how we add vectors? Nose to tail, nose to butt. You don't mind my being a little crude here. And that's how we added them together. Now we've done vector addition before. Okay, if you've forgotten, just go back and look at the tutorial on vector addition. But that's what we did in class. We physically tied a rope to the stool and we pulled in two directions. One direction with one force, okay, that we called, let's just call it here, F1. Oh, didn't want to do that. A force we called F1. And another force we called F2 over here. And when we added them together, we got a total F1 plus F2 pulling in the direction shown with the blue dots. Okay? So that is what we did in class. As you recall, the actual demonstration of what we did. Well, we got a force over here pulling in this direction, the purple one. Now that force is really made up of two vectors. It's made up of one vector, and I'll do it in red, that is pulling straight up like so. Let me undo that. It's pulling up one vector going straight up like this, and I'll make it nice and dark. One vector pulling up like that, and vectors have magnitude plus arrows, and another vector pulling like this. It is those two vectors that give us the force tension. Okay? Okay, all I've done here is change the colors to those two forces, and I think it stands out a little better. I made them purple instead of the red. So what I was saying is that It is a combination of this force pulling up this way, and let's call this force y, because it's on the y-axis, and this one over here that we'll call force minus x, because it's on the x-axis, pulling in this direction, that give us the force tension. Once I put these on there, like so, I don't need this one anymore. I could take them away, okay? But I don't want to take them away at the moment, okay? Now, we had said, now let me turn the volume here and get a little feedback. We had said that the sum of the forces, if the spot right here is not moving, the sum of the forces must be equal to 0. Well, let's make sure we write that down. That the sum of the forces, remember the symbol? Oops. Let me undo that. The sum of the forces, that symbol means sum, the sum of the forces, and if you prefer, I can draw it like this. The force total is equal to F1 plus F2 plus F3 in this case, and if we had more forces, they'd all have to add up. Now, if this point right in the center, right there, that orange dot is not moving, then all these must equal the force net, which is equal to a value of 0. Okay, so all these, force T is also the same as the force. I want to make sure that you don't confuse this. This is force total, not force tension. Sorry about that. Force total. Matter of fact, let's take that out entirely, and let's make this force net. Let's keep it at that. Sorry about that confusion. This is force net, okay? Sum of the forces is equal to the force net, which is equal to force 1 plus force 2 plus force 3. This says force net if you can't read it. Okay, but when we look at this, geez, it's not obvious how those all cancel. We know this spot is not moving. Well, what does that mean? Let's take a look at this. Let's take a look at it a little bit differently. If it is not moving, if that's orange spot, which is the same as this spot right here, which is this spot right here, if that's not moving, it implies that there must be another force equal and opposite to the one pulling down toward the ground. Well, let's draw that in a nice, pretty purple. Okay? And if that spot is not moving, it implies also that there must be another force in this direction pulling in the opposite direction to the FT2. So let's draw that also over here. Going right across in this direction like so. And this must be a force in this direction to counter this guy over here. For the time being, I'm just going to move this out of the way. I'll put it back in a second. I'm going to take this and move it over here, and this guy and move it over here. Yeah, we really don't need that. That's our force. And this is what the forces must really look like. Okay, there must be equal and opposite tugs of war. If there's a force gravity pulling down, there must be a force in this direction, equal and opposite pulling up. I'm simplifying it into just x, y coordinates, okay, to make it super simple to see. Let me show that right here, that this is the guy pulling up in this direction over here. He is equal and opposite to the force of gravity pulling down. And this one over here, if there is a vector force tension 2, which is that guy, there must be an equal and opposite pulling in this direction. Okay, as shown. Okay, I've turned this back into a plain old tug of war. Okay? And my tug of war says that this guy must be equal to this guy, so there's no motion up and down. The force tension 2, the one pulling against the wall, must have an equal and opposite force pulling in the other direction. And if we're going to label these, let's label this F in the Y direction. And I'll label this one F in the minus X direction, just so they have names too. Okay? And force T2 would be in the positive X direction. And force gravity of the bucket would be in the minus Y direction. So this is our tug of war. Okay? If you want to make it even simpler, we could do it like this. Here's one tug of war that's equal to 0. One tug of war in the X direction, where this guy, F tension 2, cancels with F minus X. And one of the wars in the vertical direction, where force of gravity of the bucket is canceled by another force pulling in the opposite direction. How do I know that? I know that because there is no acceleration, therefore all the forces must be equal to 0. Therefore, if this is pulling down with a force of gravity, there must be something else pulling up, equal and opposite. If there's a force tension pulling this way toward the wall, there must be another one in the other direction, equal and opposite. Okay, so that's another view of our free body diagram. But that certainly doesn't look anything like what we have, because if we actually draw the forces that we know, okay, let me get rid of all these. If we actually draw all those forces that we know about, they really look like this, don't they? We got a force tension pulling up over here and one pulling that way. Okay, so we're going to pause for a second, because how do we turn this nice purple into an X and a Y? An X in this direction and a Y. So I'm going to pause a second and I'm going to show you how we do that. Do you remember our coordinate systems? Our coordinate systems kind of looked like this. There was an X and there was a Y. Okay, remember? And let's label those. This was the positive Y. This was the negative Y. This was the positive X. And this was the negative X. Now let's put on there the forces that we know about right at the moment. We know that we are talking about a spot right here. And the only forces we know about is the force of the bucket pulling down, bucket pulling down like this, and we'll label it force of gravity of the bucket. And we have the other force, which I think we had in that nice pretty purple. Going kind of like this. And that was our force tension. I want to get them so that they are all on the X and Y axis. I want to turn this guy right here into just X and Y's. Now, how do I do that? Do you recall in class today I had a chair, I had a stool in class, okay, and that stool kind of looked like, let's do it from a top view looking down toward, let's say this is our stool right here. This is looking from the ceiling down. That's what we had in class. I had a stool looking from the ceiling down toward the floor. That's what it looked like. On that stool I tied two ropes. I tied a rope pulling this way and another one pulling that way. And since they both had equal magnitudes, when I was done, the end result of how this stool moved was it moved in a direction that looked like this. Now, why did that happen? Because each one was pulling with the same force, it ended up going straight. Well, this is called vector addition, and we have a tutorial on that you can go and visit. And for that tutorial, let me emphasize what we do. In order to get vectors to add graphically, okay, we have to identify, first of all, let's identify them. Here's a magnitude and an arrow showing the direction. And here was the other one, a magnitude and an arrow. To add vectors, we basically, well, all we have to do is take them and connect them nose to tail. So that's what I'm going to do. I'm taking this guy and connecting him down here. Not quite. A little bit like that. Okay, hold on one second. Okay, and when we do, and I'll put the arrow back on, when you tie them nose to tail, the end result is called the resultant. Now, we've done these before, but it's been a while since we've done them. And this is the resultant. Let's write down. This is the resultant. Two vectors added together. You just take them and move them so they're nose to tail, and that's what you end up with. So the resultant is the addition of these two vectors. Okay, so let's go back to what we had a second ago, and I said this resultant is really the addition of these two vectors. So those two vectors add together by connecting them, this guy's nose to this guy's butt, nose to tail. When you draw the third line, that's the resultant. Okay, now that we recall somewhat how we add vectors graphically, we have a vector going over here. My goal is to get that vector into an x and y equivalent, meaning two more vectors that end up doing the same thing. Well, let's see, how could I do that? Let's say that I was to pull one in this direction, like so, and I was going to pull in this direction like this. If I added those two vectors together the same way I did down here, nose to tail, let's see what we would get. Hey, it's the same thing. Now, I can move this vector, which I'm going to label as force in the y direction, and I'm going to label this one force in the minus x direction. Those are my two new vectors, and when I put those on, I no longer need to show this guy. I've got this guy pulling up, this guy pulling this way, and don't forget from before, we still have this guy down here. We still have the force T2, which is the force tension in this direction. So now I've turned this free body diagram, which just showed the forces as they existed, into forces on an XY axis. Now, I don't know what these forces are. I'm going to put this back here. I do know what this force tension is. The force tension was equal to 10 newtons. Force tension is equal to 10 newtons. And if I know that's the force tension, if I only knew here's the force Y, just moved it to that side. If I only knew this angle, then I could use this force tension to find the values of this and then once again erase it. Here's what we did in class. I said in class up on the board that we had a hidden triangle. And that triangle looked like this. Can you see this makes a right triangle? Just to emphasize it, here is that right triangle. Now, if I only knew this side and this side, I could figure out what this is. And we physically measured with a meter stick these distances. We did in class, we took our meter stick and we measured. This value, and it came out to 30 centimeters. Remember that? 30 centimeters. I'm going to not put the 30 in there. I'm just going to write the not going to put the centimeters in there. I'm just going to write the 30. And on this side, I think it was 25. Now, these are not forces. These are physical dimensions. And I said, well, if we know the physical dimensions, then we have two things, and we can figure out what this angle is over here. And we used the tangent of the angle was equal to the opposite over the adjacent. And we said this is going to be our opposite. This is going to be our adjacent. And we divided 25 divided by 30. Okay. And we got a ratio. We found out the tangent of the angle was 25 over 30. Okay, let me pick up where we were. I got interrupted there. And we found out that our ratio is 25 over 30. And we were looking for the angle, I think is where we left off. Let's choose a pen here. But we really wanted not the tangent of the angle, because that's what that is. We wanted the actual angle itself, and we know that that is equal to the tangent minus 1. The inverse tangent, that is, of 25 over 30. So let's see what we get. We've got the inverse tangent. First, before we do that, let's make sure our calculator is in the right mode. The sine of 45. Good, we're in the right mode. So, the inverse tangent of 25, our opposite, divided by 30, was 83 degrees. Oops. Looking back, I thought it was kind of large. Not 25 divided by 3. That was the tangent minus 1 of 25 divided by 30. That's a little better. So we found out our angle was actually equal to actually equal to 39.8. Let's make that 40 degrees, okay? Actually equal to 48 degrees. Okay, so we now know that this angle is 48 degrees. Okay, I'm going to take this section over here, and I'm going to redraw it now. We are done. We use these physical dimensions. Remember what we did? We took a meter stick up to the board, and we used the physical dimensions to determine the 48 degrees over here. With that, now we are done with the we no longer need the physical dimensions. We don't need the 30 and the 25. They don't do anything for us. Okay? We want to know the actual x and y component as shown here. So what I'm going to do is I'm going to take that 38 38 degrees from here. Let me go back. Was that 38 or 48? Ooh, looks like 40. Sorry about that. Good thing I caught that. I'm going to take this 40 degrees. Let's correct that. This is 40 degrees. Okay, and I'm going to go back down and place it into, don't forget what we're looking for. We're looking for actually the two forces that make up this purple line here, this bright pinkish purple line here. And all we know is that the hypotenuse is the force tension, and that's equal to 10 newtons. Okay, so let's redraw this whole triangle. I'm going to do it just right down below here. We can get rid of this now. I don't think we need what's down here, so I'm going to get rid of this. And I'm going to redraw this triangle. Okay, let's redraw this triangle. We have a line coming up like so. We have another line coming down like that, another one going back vertically across, and we can extend this purple line a little bit further, I think. And that's basically our right triangle. Okay, and we're looking for this angle over here. Actually, we have that angle over there. It is 40 degrees. Oh, didn't want to do that. It is 40 degrees. And we know this hypotenuse, which is the force tension, and that was determined because the bucket was actually, we weighed the bucket and it turned out to be 10 newtons. So we know that 10 newtons merely, this pulley merely changes the force direction, so we knew that was 10 newtons coming down. So now we're going to calculate this. And we want to know the weight of the bucket. So let's redraw this. This is our opposite over here. It's supposed to be an O. This is our adjacent. Okay, and we know, let's clean this up a little bit. This is our opposite on this side. And that's our adjacent. So once again, let's see what we have. What do we have? We have the hypotenuse. Here's what we have. We have a hypotenuse. Okay, it is equal to the force tension, and it is equal to 10 newtons. Okay, we are looking for our opposite. Okay, that's equal to a question mark because that's what we're looking for. And we have our angle, okay, which is equal to 40 degrees. Okay, and we have these formulas that say SOHCAHTOA. And we got to figure out which one of these formulas works for us. And like I always do, I go through and I check off what I have. Okay, I have a hypotenuse. Okay, this guy has a hypotenuse, so does this guy. Okay, this guy doesn't, so automatically we can cross him out of the mix. Let's erase him. We don't need him. He's not there. He's not going to help us. So we got two choices left. Well, let's see. I have a hypotenuse. Both have a hypotenuse. I have an angle for each, so that doesn't help. But I'm looking for the opposite. Well, only this one has the opposite. So it looks like this is the formula right here. Okay, because it has an opposite, it has a hypotenuse, and the sine of the angle. We know what the angle is. So let's finish this up. Okay. Let's extend the page a little bit here. And let's finish this up. We know that the sine, oops, undo that. We know that the sine of the angle is equal to the opposite over the hypotenuse. And we know that if that's the case, cross multiplying, let's see, bringing the h up to here, we know that h times the sine of the angle is equal to the opposite. And let's put in some values. We have 10 newtons times the sine of 40 degrees. Let's bring up, it's going to be equal to something. Let's bring up the calculator. We have 10 times the sine of 40. Execute. Looks like the answer is 6.2. Let's 6.2 newtons. Okay. Now let's see if that's reasonable. This is going to be our opposite side, 6.2. And don't forget, these are all vectors. There's a vector pointing up this way, There's this guy pointing up that way, and this one pointing here. Nose to tail is what created this. Nose of this guy to tail of this guy created the hypotenuse. So it looks like our opposite side is 6.2. Well, if our opposite, let's roll back to the top now. If our opposite side is 6.2, we can fill that in. Our opposite side, our Fy, is 6.2. 6.2 newtons. And don't forget that I can move this right over here. That magnitude is 6.2. So I can take that FYI, put it over Fy rather, and put this right over here so we know that it's 6.2 in this direction. This is our y component. We no longer need this over here. We're all done with this part. We don't need him. We've got 6.2 going up. What's directly opposite, equal and opposite of the 6.2? Well, the force of gravity. Therefore, therefore, this must be equal to 6.2. That must be equal, that's our weight of the bucket. And you know what? We measured it in class, and sure enough, it was almost perfect. Well, while we're here, let's find out what this F tension is. Okay, let's go back down. Well, if the sine gave us the opposite, I'll bet you the cosine gives us the adjacent. Let's write it down. And you can double check. H times the cosine of the angle, and you can work this out yourself, is going to be equal to the adjacent. Okay, that's going to be 10 times the cosine of 40 degrees is going to be equal to the adjacent. Let's pop up the old calculator. Let's plug it in. 10 times the cosine of 40, execute it, is 7.66. 7.66. Let's put that in. 7.7. We'll round up. 7.7 newtons. So that means this adjacent is 7.7 newtons. And that means if we roll back to the top, that this point right here is 7.7 newtons, which means the equal and opposite, which means this must be also, this is minus by the way, this must be equal to plus 7.7 newtons. And when we did it in class and measured it with a spring, sure enough it was. So by using our old trig functions and understanding a little bit about vectors and how they add, and understanding how this guy is really made up of two components, an x component and a y component, we were able in class to figure out exactly the weight of this bucket. And it turns out that the weight of that bucket, as we did in class, was exactly, or nearly exactly, not bad, 6.2 newtons. Now, 6.2 newtons. I'm doing this with the mouse. Let's clean that up. I shouldn't do it with the mouse. I should do it with the pen. I've got this pen here. I bought this pen. It's my pen. I want to use my pen. 6.2 newtons. See the difference using the pen? That is our answer. That's what we were looking for. But we also found that the force tension 2 was 7.7 newtons, and I'm going to put that in as well. 7.7 newtons was the tension pulling against the wall. Oops. I want to use this. 7.7 newtons was pulling against the wall. And recall, this was an actual physical example we did. We just did it theoretically now, and I showed you what we did in class. It's a little bit long, but you can take several nights to look at it and study it, and we'll be doing it over and over again. We're going to be using the same concept all the time. Okay, we're going to be doing it on several problems. So take the time, look at it, Write down any questions and please supplement your notes.